transport chain. So a couple things. The electron transport chain, it's also called oxidative phosphorylation. And so what that means is we're oxidizing the carbons, right? So we've oxidized these carbons. And then we phosphorylate ADP to make ATP. So that's the phosphorylation. So it's oxidative phosphorylation, also called electron transport chain, just to be clear. So what we're doing is we're oxidizing our electron carriers, which are NADH and FADH2, and then we make ATP. So those are the two things that we're doing. So let's look at the mitochondria. So here's our mitochondria. Here's our inner membrane. And remember, the outer membrane of the mitochondria is pretty porous.
Yeah.
Okay, but the inner membrane is not. Okay. So inside the matrix, here's the matrix. This is where we have PDC and Krebs going on, right? And then in this mitochondrial inner membrane, we have 3 key proteins, okay? And we call them complexes, right? So it can be like complex 1, and this is complex 3, and then complex 4, right, or something like that. So we have these complexes. Now what happens is these things, electrons get dropped off, and then these things take those electrons, and what they're able to do is actually pump protons, or we can also call them hydrogen ions, into the inner membrane space against their gradient. So then here in this inner membrane space, we're going to have a very low pH, which means a high concentration of hydrogen ions, right? So, so then what happens to those hydrogen ions? They want to get back across that membrane. Key concept for the MCAT, charged things don't cross membranes.
Yeah.
So these hydrogen ions cannot cross back into this membrane unless there's a channel. Surprise, there's a channel.
Yeah.
Right, and so these electrons will spontaneously, or these protons, will spontaneously flow back through this channel. And basically what they do, this has been discovered now, is they spin a wheel.
Okay.
Like a water wheel, like how a river turns a water wheel. And so they spin a wheel, and that wheel just sticks phosphate groups onto ADP to make ATP.
Okay.
So this thing is called ATP synthase. So that's our ATP synthase. So that's the general process of what's happening here. Now let's zoom in because it's slightly more complicated. So
No,
we're
wait,
gonna,
I can't see you anymore. Just not
do you want to call back?
Yeah, I'm gonna call back.
Okay.
I think it just loses connection out of nowhere.
Yeah, it's weird.
You're fine.
Okay, good?
Yeah.
Okay, so this is my inner mitochondrial membrane. here is the matrix, and here's the inner membrane space. Now we have these complexes that are in this mitochondrial membrane. So we have complex 1, 3, and 4. And then we have these little guys in between the complexes. So as far as the names go, the big guys, you can just remember them by what they do.
Okay.
The little guys, you really want to memorize their names. They're very important, the names of the little guys. So this first little guy is called coenzyme Q. You can see it as like supplements in stores, like buy CoQ because it will help your energy. And it does, it's good for your mitochondria. And then also, this little guy is super important, is cytochrome C. So so the Q comes before the C. So it's CoQ, cytochrome C. Why is cytochrome C so important? Because when a cell is dying, the mitochondria know that's happening. And they say, oh, okay, it's time to run the cell death program. And cytochrome C gets released into the cytoplasm. And that actually signals for the cell to die via apoptosis. So cytochrome C is also a signal for apoptosis. So the MCAT really wants you to know this one. Okay, so what happens? So what happens is the NADH comes in and drops off its electrons. And we're left with NAD+. So I said these things are named by what they do. So this thing takes a hydrogen from the NADH. So it's NADH dehydrogenase. That's its name, NADH dehydrogenase. So it takes the electrons from NADH. Now let's talk about, so this is a G-Chem principle, but it also applies here. So let's talk about potential. Oxidation and reduction potential. So this thing gets reduced, and this NADH gets oxidized, right? So this is a higher reduction potential. This is a higher oxidation potential. And that's going to be true of everything in the chain, right? Every time the electrons move, the thing that it moves to has a higher reduction potential.
Okay, so whatever it moves to is
Yes.
the higher reduction potential.
Yes, exactly. And the thing that gives up its electrons, therefore, has a higher oxidation potential. Okay, so we drop off some electrons here, and then, so these electrons are cool, and then this CoQ right next to it has a higher reduction potential, so it wants the electrons more, et cetera, et cetera. So we pass the electrons along. And that process, actually the point of this, so many steps here, is to not generate so much heat. Right, because remember we talked about we need a very specific temperature for enzyme kinetics and not to denature proteins and all that. So having this, and there were some weight loss drugs, I think it was called Tintin or something, I forget. Something like that, I forget, it was something like that. That actually was a decoupler. So it just sort of blocked, it allowed these hydrogens to go back through this membrane, and you didn't create ATP, so you didn't make any ATP, so you just generated tons and tons of heat, and people were dying. Because it was just generating so much heat. They were losing weight, but they would die, and it was irreversible. So people died. Okay. So we pass this electron along, and then the final electron acceptor, right, the thing with the highest reduction potential, the lowest oxidation potential is what?
I think the highest, oxidation. So is that, you're talking about wait, what, could you repeat that actually?
The final electron acceptor.
Is it the oxygen?
Yes, the oxygen.
Yes.
Right, the final electron acceptor. It has the lowest oxidation potential.
Yeah.
It has the highest reduction potential, right? So the oxygen eventually comes in and it takes those electrons in the form of hydride, right? So it's a hydride carrying the electrons. So it takes those, and then the process is complicated. I don't fully understand how the reduction, these things getting reduced, generates energy to pump protons against their gradient into here.
Yeah.
I think it's just not, the dynamics of it are just not that well understood in general.
Okay.
But we know it happens. So cool with this?
Yeah.
So there's a
It's
couple.
I think it's a little hard for me to get the ETC. I think that was like the one thing that I struggled with.
Okay.
Like in the entire like concept, but yeah, I think it's just like I'm just gonna like take time to like go through it again and again, you know.
Okay.
Yeah, I think that. Other than that, I think I got most, you know.
There's a couple more details that the MCAT likes to test.
Okay.
So we said, so let's just go over names. So we said NADH dehydrogenase, CoQ. So this thing is named for what it does,
Okay.
right? So it takes electrons from CoQ. So it can be a CoQ oxidase, or it can be a cytochrome C reductase. You can call it either one. So it's a coenzyme Q oxidase or a cytochrome C reductase, right? Because it gives its electrons there. And then this one could be called oxygen reductase, but for some, I like that name, but people don't like that name.
Yeah.
So they just call it cytochrome C oxidase. I think oxygen reductase sounds cool.
Yeah.
But some people don't think so. So it's just called cytochrome C oxidase. So those are the names, just to be clear on the names. And then this FADH2 that we made at the end of the Krebs cycle, so that drops its electrons off at CoQ. So because of that, you get fewer ATP per FADH2. Now that's an easy concept to understand. Here's the wrinkle that the MCAT loves to test. So this NADH that we made all the way back over here, this has to be transported into the mitochondria.
Okay.
So when it's transported, it can only be dropped off here. So we call that glycolytic NADH. It gets dropped off at this CoQ. So for the glycolytic NADH, we get fewer ATP per these Krebs cycle NADH, because these are already within the matrix, right? Whereas this is in the cytoplasm, has to be transported in, so it gets dropped off here, so we get fewer ATP per glycolytic NADH. Now, the real wrinkle is that prokaryotes don't have to do that. Because prokaryotes do this, not across an inner membrane in a mitochondria, but across their plasma membrane, this glycolytic NADH in prokaryotes can be dropped off here at NADH dehydrogenase. So for prokaryotes, they're actually more efficient. So per molecule of glucose, a prokaryote, so the numbers are kind of skewed. I don't know what numbers to believe, but let's just use 30. So per molecule of glucose, a prokaryote will make 32 ATP if it went through this whole cellular respiration cycle.
Yeah.
And a eukaryote, because of this inefficiency, will make 30 ATP per glucose. Right, and that's because the glycolytic NADH gets dropped off at the CoQ, because the CoQ is in the mitochondria. Is that clear?
Yeah.
Okay. Great. Now I have some math in the notes, but that's honestly not important. So let's, for the sake of efficiency, let's not go into that. And we already talked about fermentation. So I just want to make sure we go over that again. So in the case where you're not using oxygen, so if you don't have this oxygen here to be the final acceptor of these electrons, you can't do any of this. So that's the importance of oxygen, is that it takes these electrons and so it allows you to do all of this, because you get to replenish this NAD plus that then can then feed back here. If you can't do that, then you have to ferment. And when you ferment, you only get 2 net ATP per glucose. Right? So it's a big difference between 30 or 32 for prokaryotes and 2. So that's how efficient, but most of the time, we're actually fermenting. We don't really use oxygen that often unless we're really exercising. And it takes a while to turn that on. That's why like the first couple minutes of exercise are always the most difficult. We're always like, man, I'm so tired. I've only been running for 45 seconds. But then once you get going, you're like, oh, okay, now I can go. Because now all this is turned on.
Yeah.
Okay, and so what happens when you don't have oxygen, so like when you're doing high intensity interval training, NADH builds up. And NADH is the big regulator of the Krebs cycle. So when NADH builds up, the Krebs cycle just sort of grinds to a halt. And then all you can do is glycolysis. And that's what happens in alcoholics. So alcoholics, they drink so much, they change. So a lot of this happens in the liver. So alcoholics drink so much that they change the metabolic state of the liver, and they create so much NADH, it actually inhibits the Krebs cycle.